Hello students, let's do this last example of a force problem. This one is a little bit more tricky than the others just in the way that we set it up, but it has, believe it or not, a much simpler answer. And I know when you're looking at it, it seems like we do not have enough information to solve, but I promise you that we do. So for this problem, we have late in the season skiing, and we're going down the hill and it's not very steep. And the angle of the hill is 28 degrees and we're moving at a constant velocity. And just knowing that, we want to find out what is the coefficient of kinetic friction. So what I'm going to do, I'll draw my free body diagram, but this time here, I'm going to draw it so that I have a little bit of a tip on my axis. So I still have my X and the Y. Here's the ski slope, still going to be on the X axis. Now right here is my angle. This is 28 degrees. Here we go. And gravity always pulls straight downward. Right? So that's FG right here. And so we can see that this angle is also very similar because it is the same as our ski slope. Right? Remember, the trick is to not tip this too much. So we can see that this angle here along the axis is the same as this one. Now, for this problem, we are moving at a constant velocity down the ski slope. Our force of gravity is not on an axis, so we have to put it on the axis. So to do that, just like in previous problems, we'll have to resolve this vector into its x and y components. So here's the force of gravity's x component, and here is the force of gravity's y component. So it's this small x component, that almost looks like a y, let me fix that. But it's that small x component here that's pulling us down the ski slope. It's the y component that's keeping us planted on the hill. Since we are on the surface, we still have our normal force, and we're moving at a constant velocity. So I've got my kinetic friction balancing that. And the problem is asking us to find what mu k is equal to. There's no mass, and you're thinking that we don't have enough information, but let's do this. Let's trust that the problem-solving steps for these force problems will help us. So the next thing to do is to sum up all the forces on both axes. So let's do the x-axis first. I've got the x component of gravity pulling us down the hill, minus Fk equals 0. I need this part here. I'm going to solve it for Fk because I know Fk is in my force of friction equation. So Fk equals Fgx. And we know that Fg is always equal to mg. And if we look at the diagram over here, this x component, it's really the same as this dotted line. So that would be the opposite side. So I'll use sine theta. Next, let's go over to the y direction. On the y direction, I have the normal force upward, and I have the y component of gravity pulling us downward. Again, I equal 0 for this. We're technically at rest on the y-axis. So I'll look at this part here, and I can see that Fn equals Fgy. Fn equals, Fg is always equal to mg, and the y component here is along our angle. That's the adjacent side, so we use cosine theta. And some of you might be able to see how we can solve this without using the mass. We know that the next step for these force problems is to use our friction equation. So mu k equals Fk over Fn. And for this problem, I need to do substitution. What I have for Fk goes here. What I have for Fn goes underneath here. Just erase that. So Fk equals mg sine theta. Fn equals, I keep erasing that, mg cosine theta. And look what happens. Masses cancel, little g cancels. In fact, what does sine over cosine give us? Let's say you didn't remember. You could still do this problem because the only piece of information we have is the angle. But if you did remember, sine over cosine is tangent. And so look at how this equation simplifies. Tangent of my angle will give me the coefficient of kinetic friction. So tangent of 28 degrees means that we have 0.53 for our sticky late season snow. So rely on the problem solving steps. They will not let you down. And I will see you in class.